The next speaker is Francisco Mazzitelli from Bariloche Atomic Center, Argentina, and he's going to talk about shortcuts to adiabaticity in the dynamical Casimir effect. Francisco, thank you very much for coming. It's a pleasure to receive you here. Thank you.
Thank you very much. I would like to thank the organizers for inviting me to give this talk. And I really apologize for not being able to travel to Brasilia today. So happy birthday, Victor. I think that we met for the first time at the International Workshop on the Dynamical Casimir effect in Padova. And then we met several times over the years in the series of workshops on the quantum fields under the influence of external conditions. And also I remember you organized a very nice meeting for the 60 years of Casimir effect in Brasilia. More important than that, I learned a lot of physics from your papers, and I can mention your review paper on the dynamical Casimir effect in 2001 that was very useful for me, for my colleagues in Argentina, and also for many of my students, as well as other papers on the vibrating cavities and dynamical Casimir effect, from which I learned a lot. So thank you very much, and my best wishes. So I will start with my presentation, which is about shortcuts to adiabaticity in the dynamical Casimir effect. And this is the outline of the presentation. I will first make an introduction and motivate the investigation. Then I will describe briefly the shortcuts to adiabaticity for a single quantum harmonic oscillator with time-dependent frequency, to move them for the case of the quantum field theory, a general discussion on shortcuts in quantum field theory. And finally, the main topic of my talk will be to talk about the shortcuts to adiabaticity in the dynamical Casimir effect. This is work that we have done in last year and the present year with my colleagues, Nicolás del Grosso, Fernando Lombardo, and Paula Villar, all of them at the University of Buenos Aires. Okay, so the topic of interest is quantum non-stationary systems, and in particular, in the context of Casimir and related effects. So situations in which the vacuum polarization, the vacuum fluctuations are relevant, and one has external time dependence. If we have a non-adiabatic evolution, then we have a large number of very interesting phenomena. And in this context of the Casimir physics, we have dispersive forces, and we heard the other day a talk by Roberto Passante on modifications to the Casimir-Polder interactions in the presence of time dependence. Then we can have dissipative forces like quantum friction or forces on atoms and moving mirrors. And we can also have the effects like the creation of particle or motion-induced radiation, or what is called the dynamical Casimir effect. And we had the previous talk by Danilo Alves, which reviewed this topic. So the question is, can we avoid these effects? Can we avoid these non-adiabatic effects? Okay, then one can say, okay, yes, you can. You can if you perform an adiabatic evolution. But the adiabatic evolution should be very slow, very, very slow, in order to be adiabatic. And then the next question is, can we do it fast? Can we find a fast road to an adiabatic evolution? If this is the case, then we say we have a shortcut to adiabaticity. So it's a way to control the system, to start from a given state to end, to basically the state which would correspond to an adiabatic evolution, but in a short time, not in a very slowly evolution, but in a short time. Okay, so this was proposed for the first time by Chen and others in 2010. And there was also Adolfo del Campo, which is one of the leader experts in the field and gave a talk this morning. And the question is, okay, I have here a cartoon to illustrate the situation. So imagine you have a system with some energy levels here. And then if you have an adiabatic evolution, which is here in red, I don't know if you can see the mouse, but the red lines, you have that the system follow instantaneously the energy level, the instantaneous energy level. But you can have a non-adiabatic evolution, like this blue dashed line in which the system is excited. And then you can have this shortcut to adiabaticity, which is the green one, in which you start at the same point that in the adiabatic evolution, and you end at the same point, but following a shortcut. I mean, in an evolution which is shorter in time than the adiabatic evolution. So why are these shortcuts to adiabaticity of interest? Well, mainly because you may want to have control of quantum systems, and for instance, you can avoid decoherence by using these kinds of evolutions, or you can improve the efficiency of quantum machines. And there are many, many examples of shortcuts in different areas of physics. For instance, in the physics of trapped ions, cold atoms, Fermi gases, Bose-Einstein condensates, etc. So, but in my talk, I will be talking about shortcuts in the context of quantum field theories. And the motivations are, there are different motivations. On the one hand, and this is my main motivation, is the conceptual interest of understanding some aspects of quantum fields under the influence of time-dependent external conditions. Then there are other more specific interests. For instance, one might think of quantum machine based on quantum fields, and I will talk about this very, very briefly. Then you may have situations where you may want to avoid particle creation. For instance, you can have quantum electrodynamics in the presence of strong electromagnetic fields, and you may want to design the fields in order to avoid particle creation, to avoid the excitations of the field. And then there are other more theoretical interests, which is, for instance, which has been mentioned last year by Tanmay Vachaspati, which you have in QCD, you may have stability of some electric flux tubes that may help to understand the confinement, for instance. So there are several motivations to study this, and in this talk, I will be mainly concerned with this shortcuts to adiabaticity in the context of the dynamical Casimir effect. So this is the introduction to this talk. So let me first review how we can have the shortcuts for the case of a quantum harmonic oscillator with a time-dependent frequency. Okay, so I will say here very, very basic things. We have the equation of motion for the harmonic oscillator, and we can expand the momentum, the coordinate operator in terms of creation and annihilation operators. And these functions here, Q of t and the complex conjugate, can be written in this way in terms of real function big W. And this is not up to now no approximation. It's just to impose that the function Q of t should have the adequate Wronskian in order to the creation and annihilation operators to have the correct commutation relations. So then the equation, the dynamical equation of Q becomes a nonlinear equation for W, which is this well-known equation. We can have a situation where the frequency is asymptotically constant in the past and in the future. So assume that the time-dependent frequency goes to omega in for t going to minus infinity and goes to omega out to tau going to plus infinity. So in this case, we can define the in and out solutions to the equation of motion that are the solutions that have this behavior in the past and in the future. Of course, if I have the in solutions and the out solutions, they are both solutions to the same equation, so there should be a Bogoliubov transformation connecting them, and these coefficients alpha and beta are the coefficients associated to this Bogoliubov transformation. Then if I can build the Fock spaces, the in and out Fock spaces, and they are related, of course. And if I write the in vacuum, the in ground state in terms of the out state, then I have a squeeze state in general, unless the beta coefficient of the Bogoliubov transformation vanishes. And of course, the other well-known point is that the mean occupation number of the out states in the in vacuum is given again by the square of the modulus of beta square. Then I say, okay, what happens if you have an adiabatic evolution? If you have an adiabatic evolution, then you can write the solution for Q of t in this way, and to solve this nonlinear equation by neglecting the derivatives of W here, I'll say that big W is more or less equal to the frequency. This is an approximate solution. But then the main point that was stressed by people working in the shortcuts to adiabaticity is that you can use what is called the reverse engineering to find adiabatic shortcuts. I mean, you can force that a solution of this form, to be an exact solution of the problem if this reference frequency satisfies the equation which is written here. So I say, I force that the Q of t written here to be an exact solution, and then for a given reference frequency, and this will be an exact solution of the problem with this effective frequency, which is written here. So this is the reverse engineering. I propose a solution, and I see which is the frequency that makes this solution an exact solution of my problem. So let me, at this point, introduce the Markov function. This is an equivalent way of saying the same thing. If I write rho equals to 1 over square root W here, this is the Markov function, satisfies the Markov equation, which is equivalent to the previous one, of course. And the main observation that was made by a very, very nice paper by Lewis and Riesenfeld in 1969 is that if the frequency is constant in a given interval, then the Markov function in that region is a constant plus an oscillating function. Okay? So this is very important. So I will I take a plot here from this reference, from this PRL. So here you can see two Markov functions, one in which it is initially constant and at the end is an oscillating function. And this corresponds to the case and the volume transformation is non-trivial. And the in state is an out, is a squeeze state when written in terms of the out states. And the second evolution corresponds to a non-exciting evolution in which there is no exciting of the harmonic oscillator, and the harmonic oscillation is at the end, it's again in the ground state. So these oscillations have all the information on the volume transformation. And remember this because this will be very, very important. So you can find shortcuts to adiabaticity using reverse engineering by choosing a reference Markov function that tends to a constant both in the past and in the future, and then compute the effective frequency from the Markov equation in this way. So these are the shortcuts for the harmonic oscillators. I think I will skip this. And I will move to the case of shortcuts to adiabaticity in the context of quantum field theory. So quantum field theory, if you have a free field, then you have a set of coupled harmonic oscillators. If you have an external time dependence, then you will have time-dependent frequencies and time-dependent couplings between the different oscillators. For instance, if you have in the dynamical Casimir effect in 3+1 in 3 dimensions, for a scalar field, you have equations of this kind that in which the modes of the field can be written in terms of a set of coupled harmonic oscillators with time-dependent frequencies. Of course, this is a very, very complex problem, and if in some cases people has worked using a single mode approximation, and of course, if I neglect the couplings between the modes, I consider only one mode, then I can apply all the results for the quantum harmonic oscillation I mentioned before. But I would like to consider more complex examples because a single harmonic oscillation does not have the full aspects of the quantum field theory. And then the next example in which you can have the next example in increasing complexity is to consider a quantum field, a free quantum field, in the presence of an homogeneous background. So in that case, you have a set of uncoupled oscillators with time-dependent frequency, and which every oscillator corresponds to a different Fourier mode. For instance, you can have QED in an external time-dependent electric field, and the frequency of the Fourier modes is given by this expression. Or you can have quantum fields in an expanding universe, for those of you who have studied problems of quantum fields in semi-classical gravity. And then in this case, you will also have a set of harmonic oscillations with time-dependent frequency. A short comment here is that note that here you will not have excitation if the frequency does not depend on time. And this happens when the fields are massless or when the coupling to the curvature is 1/6. And this corresponds to conformal invariance. I will, just for those of you that this tells something for you. Then we can also have fields which are coupled to a classical scalar field. So you have several examples when you have this set of uncoupled harmonic oscillators. So I will skip this. And Okay, and can we see another more complex example? Yes, we can. If we consider, for instance, massless quantum fields in weak inhomogeneous background, then it has been shown that the vacuum persistence probability, I mean the probability for have particle creation, is proportional to this expression, which involves, which is called the Ricci scalar and the Weil tensor. And again, the main observation is that there is no vacuum excitation if there is conformal invariance, which in this particular case means conformal coupling and vanishing of the Weil tensor. So this is one of the reasons why we decided to study the shortcuts to adiabaticity in the dynamical Casimir effect in one dimension or in 1+1 dimensions, because we know that there conformal invariance plays a crucial role. So we now consider the main topic of my talk, which is the system which has been discussed in the previous talk, which is a one-dimensional cavity, a scalar field in a one-dimensional cavity with a Dirichlet boundary condition. So the field satisfies the wave equations in 1+1 dimensions and the Dirichlet boundary conditions. I will be assuming that the two mirrors can move in principle. So this problem, thanks to the conformal invariance, can be solved using the approach by Moore. In this case, because if you have two moving mirrors, you need two Moore functions instead of one when you have only one of the mirrors is moving. And then basically what you have is you introduce two functions, G and F, that implement a conformal transformation that map the moving mirrors into static mirrors. And the functions G and F should satisfy these two equations that are written here below. So if you know the mirror functions, then you can have the field modes, which are written here. And the main observation here is that if the cavity is static, so for instance, if you have that the left mirror is at rest at x equal to 0 and the right mirror is at rest at x equal to d0, then the Moore functions are equal and are a linear function plus a periodic function. So here has the first main message of my talk. There is an analogy between the Moore functions in the dynamical Casimir effect and the Markov function for a quantum harmonic oscillator with time-dependent frequency. And the analogy is the following. If you have a time interval in which nothing depends on time, then the Markov function is a constant plus an oscillating function, and the Moore functions are a linear function plus a periodic function. Or if you want, the derivative of the Moore functions are a periodic function, a constant plus a periodic function. Okay, so this analogy is very interesting, and the main point is that the periodic function in the Moore function or the periodic part of the Markov function have the information on the excitation of the system. So we can also, in the case of the dynamical Casimir effect, use reverse engineering to find a shortcut to adiabaticity. That is, to find evolutions of motions of the mirror that at the end do not produce particles. Right? This is the way of finding the shortcuts. So you propose a Moore function or more functions that are linear in the past and in the future, and then you compute the trajectories from the Moore equation. Once you have the Moore functions, then you can compute the energy density inside the cavity using these complex formulas that were derived originally in the paper by Fulling and Davis in 1976, and then were generalized to the case of two moving mirrors in this reference that I am including here. So if you have a single moving mirror, we will assume that the right mirror is moving and the left mirror is at rest. Then you have only one more equation. And then you have that you can define a reference motion. Assume first that you have a reference motion which is slow. So you can define an adiabatic Moore function, which is written here. And then you can say, okay, this adiabatic Moore function will be an exact solution of the problem for a different trajectory that I will call R effective, if the R effective satisfies the Moore equation in this way. So I give a reference trajectory, I compute the adiabatic Moore function, and then I compute the effective trajectory that implements the shortcut using the Moore equation. This is exactly analogous to what we did for the case of the harmonic oscillator. Just a comment that you can check that the trajectory that you get from this adiabatic Moore function satisfies that the velocity is always less than 1. So we're using natural units. That means that the velocity is less than light velocity. So this will be, in principle, a physical trajectory. So I can show you here, so the first results. So assume you have a reference evolution, a soft reference evolution, which is this line, the blue line here. So this is our reference, and this is we choose a smooth function in order to avoid the singularities that appears in the energy momentum tensor if we have jumps. And then we computed the effective trajectory, which is this dotted red line here. And so for this trajectory, there will be no particle creation at the end. And you can see this in the energy momentum tensor, in particular in the energy density inside the cavity in this plot here. What we are seeing here is the following, and this is also has a lot of connections with the results of the previous talk. At the beginning, we have the static Casimir energy, blue here. Then when the mirror starts moving, you have a pulse of electromagnetic pulse, the radiation inside the cavity. You have the photons there. And then when the pulse bounces in the static mirror and comes back to the moving mirror, the motion is such that all the photons are absorbed in the mirror, and at the end, we have again the static Casimir energy. So for this particular effective motion, we have no particle creation at the end, but we do have particles during the evolution. So the particles are created and then absorbed. So this is a plot of the ratio of the full energy density, inside the cavity, and the adiabatic energy, which is essentially the Casimir energy, the vacuum Casimir energy, or the vacuum Casimir energy plus the thermal energy if we consider a static non-zero temperature. And of course, this ratio starts at 1 and ends at 1, because at the end there is no created particles, so we come back to the original situation. Here are plots for different values of the temperature, but the important thing that you should see here is that the dashed lines, which corresponds to the effective trajectories, start at 1 and end at 1 also. There are some other results related to this. One is the example discussed by Folling and Davis in 1976, and that was described in the talk by Danilo Alves. And again, you can have that for some, you have the mirrors that are at rest, that one starts moving with constant velocity and then stops. And then there is a particular time such that the particles created when the motion starts are absorbed when the motion ends. And there is a very nice connection between this result and our result because we have proved that this effective trajectory that absorb the particles corresponds to an instantaneous jump for the reference trajectory. So if we choose an instantaneous jump for the reference trajectory, we find an effective trajectory, which is that of Folling and Davis. There was another paper where this was discussed by my professor Mario Castagnino and Rafael Ferraro, that they call this motion with continuous velocity and no particle creation. So again, there was the same idea, just propose a Moore function which is linear asymptotically in the past and in the future, and you will find a motion with no particle creation. So the main messages so far are the following. There are non-exciting evolutions for a moving mirror in a one-dimensional cavity. This is a first non-trivial example of a shortcut in quantum field theory under controlled external time-dependent conditions. There is an interesting analogy between the Markov function for a quantum harmonic oscillator and the Moore function for the dynamical Casimir effect. And this is the way one can imagine how to construct the shortcuts using reverse engineering in the case of the dynamical Casimir effect. And the other message that I did not discuss, but I would like to stress, is that, of course, there are no shortcuts for a single mirror moving in vacuum, just one mirror, not a cavity, because if you move in mirror, you create particles, and the energy of the created particles is always positive. So if there is no bounce at some point, you cannot absorb the particles. So you need a cavity to have these shortcuts. So this is the main point. I have other results that I will describe very, very briefly, but this is the main messages I wanted to transmit. So I will skip the auto cycle. So we generalized these results for the case of two moving mirrors, in order to have more tools to control the energy density of the photons inside the cavity. In the case of two moving mirrors, we have two Moore functions, and we needed to generalize the results in the original paper by Moore in order to compute the adiabatic solutions for the Moore functions. We did it. The details are not necessary here, but please look at these results where we have F adiabatic and G adiabatic. So we have that the adiabatic solutions are given by these expressions here. And this, of course, if you do a systematic adiabatic calculation, you will find there additional corrections which are proportional to the derivative of the R and L functions, so the trajectories of the left and the right mirror. So in the same way we did it for one mirror, we can define by reverse engineering shortcuts to adiabaticity for the two mirror cases. So the complication is that we have in this case, we have two Moore equations, and we did it, and I show here some examples. For instance, in this graph, what we are seeing is in the left plot. So the yellow line is the reference trajectory, and the blue line is the effective trajectory. And in the bottom, we have that the black dotted dashed line are the reference trajectory, and the red dashed line are the effective trajectory. So we have reference trajectories for the right and left mirrors, and effective trajectory that implements the shortcut. So for these trajectories, we don't have particle creation at the end of the motion. Here in the right plot, we have the plots of the Moore functions. But this is essentially what I wanted to say, that is that we can do that, the same kind of things for two moving mirrors. This is for a symmetric contraction, and we did it the same for a symmetric expansion, and we did it the same for a rigid translation of the cavity. So we can have as the reference trajectories a rigid translation, and then the effective trajectories, which are not rigid, implement the shortcut. I mean, what implement is that the fact that at the end we will have no particle creation. And the last point in my talk is that we also studied the following problem. Assume that we have a motion that creates particles. Can we do a subsequent motion in such a way to absorb the created particles? And we call this the shortcut to adiabaticity completion, or particle annihilation. And this can also be done. And in fact, in this slide, what we are showing is the case of a harmonic oscillator. If we have an harmonic oscillator that in the first motion goes from an in frequency to an W omega minus to omega plus, and we have a squeeze state, then we can implement an anti-squeezing in the case of the harmonic oscillator by a second trajectory that goes to a final frequency. And the way of doing it is very easy. Just complete the Markov function. So we have an Markov function. Remember that is a constant plus an oscillatory function. And then we can complete the Markov function in order to come back to the original frequency. And the whole Markov function describes a shortcut, because at the end there will be no excitation, because the Markov function is constant at the beginning and constant at the end. And we did it also for the case of the dynamical Casimir effect. So I show you here one example, and in which we have a first motion that creates particles, and then with this second motion of the cavity, we can absorb the created particles. So the second motion makes a change on the Moore function, and everything combines in order to have no particles at the end of the motion. So I think I am running out of time. So I had other generalization and other properties that if someone is interested, we can discuss later. But I think I will run to the conclusions. This were only just applications of the same idea. Let me just show this one, in which we have a motion of the cavity that, in this case, that initially create particles. The initial motion creates the particles here. Here you can see the energy density.